Still not on the on-site conference, but maybe someday we will eventually meet. So thank you, Oren, for being with us. I'm super interested in your talk about scaling things because scalability is the king. So I will not prolong this introduction further. The scene is yours. You will probably introduce yourself more better than me, so I'm hiding and listening. Thank you.
Okay, thank you very much. My name is Oren Eini. I'm the CEO of Hibernate in Rhinos, and the primary product that we produce is RavenDB, which is a document database written in .NET. I'm not here to talk about that. I'm here to talk about architecture and how you can create an architecture that is scalable. Well, that's the topic of the session. That's easy. But let's talk about what it actually means. And I really love this definition of scalability. And the basic idea is very simple. It's scalable if we add more resources to the system. If we double the resources in the system, we double the capacity. If we added 50% to the system, we have another 50% to the capacity. That's it. Anything that doesn't match this is not scalable. But, this is for 2006. That's old news. Who cares about that? We're now in the cloud. We are infinitely scalable. Why do we care about that? I mean, I can write a Lambda and trust Amazon to ensure that if I need to have 100,000 invocations, they would provision the hardware and do the magic necessary to make it happen. I just need to foot the bill. So why am I talking about scalability? We have serverless now. We have auto scaling. Now, is this my problem? And I want to go back in time. Not a lot of time. 1998. This is in the Museum of Computer History, and this is the fourth server rack at Google. Now, I want you to take into account this is the specs. 2 CPUs, 300 megahertz, half a gigabyte of RAM, 90 gigabyte of disk across 10 different disks. Just to give you some idea, this is a Raspberry Pi. This is a Raspberry Pi 400. It is massively overpowered compared to that, and that is what Google used for quite some time. So I want to give you some notion about how this works. A while ago, I wrote this. And if you go look at my blog, I have a series of topics where I'm talking, blog posts where I'm talking about high-performance.NET. So I wrote a Redis clone. This is the advanced version. It's about 200 lines of code. And I'm running that on a Raspberry Pi. So this is the relevant machine. You can see 4 cores. This is the memory that we use. And this is the machine in question. I'm going to run my Redis clone. And on my machine, I'm going to run benchmark for Redis. And I notice that we are processing 173,000 requests per second. And look what we have here. This is running under quite some load. And look here, P99 percentile, processing 170,000 requests per second. This is .NET running on Raspberry Pi, handling 170,000 requests per second, not being optimal. This is absolutely not an optimal solution. Let me run this again to give you some more context. Now running that for 60 seconds, and what you will notice is that we are at 100% CPU. Let me just do something. Going to run it from scratch so you'll be able to see exactly what's going on. Because what happened is that the queue is full and we're spending a lot of time there. What we notice now is that the red part is kernel time. The green part is user time. So we actually are at high CPU, but most of the time we're spending at kernel. This is because I'm not using an optimal solution here in terms of IO. Because this is, dear God, this is me running 200 lines of code, not being super optimal. And why am I talking about performance when I'm talking about scalability? Those are not the same. I wanted to stop on that and give you why it matters. And it matters because of one simple reason. This is, by the way, I'm running that, I ran the benchmark previously. I ran that on better network. And you can see that close to 200 requests per second at P99 of under 100 milliseconds. And that matters because in many cases, the computer is not a problem. This is not that, oh, we are limited by hardware resources. Just to give you some context, 200,000 requests per second is enough for 99.5% of all websites in the world. Period. So, and I can run it on Raspberry Pi. You could run all of Google in the early 2000 on a bunch of Raspberry Pis. It would be massively overpowered. So when it comes to time to build a scalable machine, scalable system, the easiest way is to just throw hardware at this. Make this bigger, make it faster, stuff like that. My position is that this is absolutely the wrong way to go about it. It used to be the case that you had to go into super scalable system because, well, the machine couldn't run. Now you have the ability to get machines big enough, fast enough that it doesn't matter. And most of the time we spend doing a lot of work at the critical part. So let's talk about how we can prevent that, not by being super optimal. Let's optimize every line of code that we have. Let's write everything in assembly and use simple instruction, all sort of stuff like that. That part lies madness. Let's talk about how we modify the overall architecture that we have in order to get good results, fast results. One way of doing that is to get a time machine. Figure out what you did wrong and prevent that. Unfortunately, my time machine is currently broken, and I use the term very, very properly. So let's look at how we can learn without a time machine. And the whole point is that we can start looking at what other people did. And there are blog posts and books and a whole bunch of material around that. But the key here is that your scenario is likely different and things change. And one of the most annoying things that I notice is that you can have a very scalable system for the initial solution. And as things grow and you have additional requirements, suddenly the same process become untenable. For example, looking at Twitter, hashes and mentions were not something that Twitter thought about. They just pop up from the way users use the system. But think about what it means in terms of how Twitter needs to now process a tweet. It needs to scan for mentions so it could put that in the right timelines. It needs to put the hashes in the right place. Okay, that's additional processing that wasn't accounted for. Are you going to meet your SLAs? Which leads to another interesting observation. What is your architectural style? You're going to have domain-driven design, command query responsibility separation, event sourcing, whatever the buzzword of the day is. All of them end up being super complex when they are applied across the board. The fourth question that we need to ask when we need to talk about scalability and performance is, what is the SLA? So look at this. This is a fairly common SLA. The page should load in under 200 milliseconds for 99.99% of our users. This is a good SLA. It's not a great SLA. We touched exactly on why before in a bit, but it's a good SLA. Why? It's measurable. It means that I can tell, yes, we are hitting this SLA or not. I want it fast is not a good SLA. I want it to be as fast as Google. I want it to be just like Google. Is not measurable. At one point, I asked a client, give me the Google budget. To be read more, it's like I sent them a quote for something like $60 billion. And apparently I broke their entire internal system doing that. And but it got the point. I cannot work without some number to guide. So why isn't this a great SLA? It's not a great SLA because it's missing another number here. And that number is under what load. If my system is expected to run under 1,000 requests per second, I can meet this load. What if I have 10,000 requests per second? Do I need to worry about this time? The end result is that we want to define exactly what's going on and how this is happening under different scenarios. And in most cases, you would see that people says, oh, you should plan for the next order of magnitude increase. So if you're now deploying to 100 users or 1,000 users, then your architecture should be sustainable until you get to 10,000 users. And that sounds okay, but then you realize that the jump from 1,000 users to 50,000 users can happen very quickly. Not touching on politics, but touching on technology. In end of 2020, there was the social network Parler, and they were adding 50,000 users per day on the ramp up to January 21. That's an insane level of growth. Completely unsustainable in terms of the kind of architecture that you have. And there are a number of cries for help. They were booted from AWS at one point, and they needed to go to another provider very quickly. And the servers that were using were leaked, the specs, and they were running on thousands of servers, which I find absolutely insane given what they were actually doing. I actually wrote a 10 parts blog post series on how to create a large-scale social network without breaking the bank. So the second important rule is, don't write checks that you can't cash. What does it mean? When you implement features and you're predicting, oh, I will replace that when I have the next order of magnitude growth, if you're actually successful, you don't have the time to do that. You're too busy putting down files than being able to actually recover from that, to actually do a whole re-architecture. See also Twitter and around 2008, where the fail whale and the slowdowns and everything and Twitter doesn't work was the running joke. GitHub in 2015, same thing. Very slow, doesn't work because replacing the architecture behind the scenes is super complex. But you don't need to do that. So let's talk about what is the number one cause for this. And this is one common pattern. You're doing something expensive in a critical path. So let's talk about what is a critical path. Critical path for me means that the user is waiting for that. Because when you have a user, there is a built-in timer. Eventually they get tired and go away. And the damage to your reputation is huge to the point where 15 years later, when I think about scalability issues, I think about Twitter in 2008, 2007. Think about the impact of that. So you don't want to do anything critical, anything expensive in the critical path. The user is waiting for you and you have a budget. And the budget is small. So let's talk about this. What kind of critical components do we have that we have to run them while the user is waiting? Oh, I have to go and run a query, and that query is expensive. I have to go and query, I have to touch a third-party system. I have no control over that. Well, if you think about the scalability of your solution, every time that you have something that is expensive in the critical path, this is a guaranteed for someone having a bad day. But how can I prevent that? Well, to start with, I should be able to measure what's costing me. I should be able to say, hey, this is what's costing me here, this is what's costing me here, stuff like that. The problem here is that most cases you have dozens of such systems with very subtle interactions and very hard to tell when something is happening. So let's talk about a different way of doing that. Instead of writing a check that I have to cover immediately, let's make a payment plan. Let's make sure that I divide the world into the expensive and the cheap things. It's cheap to get the data by ID if I have a key. The example with Redis is a great example. Look at this guy. Raspberry Pi, 170,000 requests per second, and look at these latency numbers. I like those latency numbers. They're nice. Even under this load, if I had one query per page, I would still be able to handle that, and that's me serving almost 200 requests per second. 200,000, sorry. If I'm querying over a simple index, if I'm touching the local database, and that's actually really important. I'm a database guy by trade, and one of the things that you want to have is every application has its own database. It may be residing on multiple machines, but it's local to this application. It's not, oh, someone is running the daily report, so the entire system slows down. This is a separate system. And that system is sitting nearby to my application. In 2018, GitHub had an outage of 24 plus hours. Why? They have a network partition. That network partition redirected traffic from a web node in the East Coast to the database nodes on the West Coast. It's an addition of about 30 milliseconds of latencies in terms of network round trip. The entire site went down because the underlying system assumed that they could make multiple queries to the database because the local database was nearby and there was no network latency. Once you have the latency between the East Coast and the West Coast, the entire thing went down because the request took so long that either the user gave up or they were timed out by the underlying system. Another thing that is really cheap is if I have a small bounded amount of work. I'm processing an item, a small set of items. Not I'm processing John invoices for reimbursements And John is the guy who just came back from 6 months in Taiwan, and he's going to submit all of those invoices all at once and choking the entire system. Putting stuff in a queue is really fast. Keep that in mind. That's going to be very, very, very important. Things that are important, things that are expensive, anything that is complex queries, touching third-party systems, stuff like that, those becomes untenable, especially when you grow, because growth happens at two axes. You have more users, more data, and everything, and the complexity of the system grows as well. So you actually have 3 or 4 dimensions to manage all at once. So let's talk about this. I don't want to do expensive things, but I still have to do them. How can that happen? Well, the idea here is that I don't want to do the expensive things. I don't want to do the expensive things at the critical path. It's cheap to put things in a queue. It's trivial to scale. Queues are horrendously easy to scale. Every platform have that. If you're running on AWS, Azure, you have the built-in queues. If not, Kafka or RabbitMQ are available everywhere. And that means that you have a strong separation of putting something in the queue and processing that. Okay, so every time that I have something that I can't do trivially, I throw that in queue and handle that later. But look here, this is an important user experience concept. We don't promise to do something right now. We say we accepted that and we will process that. In most cases, we may process that right away. It's slightly more complex because instead of sending a request and getting the result back, we send a request, we get accepted, we're good, and then we have to poll or get an event or something that this was done. But this is not too complex to do, and it pays off a lot when you grow, because scaling a queue is trivial. It also means that any online operation, anything that happens in the critical path, cannot do a lot of work. So you have to prepare things for in advance. This is similar to event sourcing, but on a completely different topic. I'm not doing that to organize my data to have a better structure. I'm doing that because I don't have the time. I don't have the capacity to do more complex things. And the front end does very little. The front end just needs to say, oh, for example, if I'm sending a tweet, and if think about it, if I'm sending a tweet, that's actually quite complex because I have to do the mentions and hashes. I have to check if you are posting images that are not acceptable in the network. I have to maybe do OCR to see if you're trying to load a banned topic. There is a non-trivial, maybe you're using spam or fraud or whatever. There is a non-trivial amount of work that needs to be done. But the concept, the SLA for me hitting submit or sending a tweet until you see that is measured in seconds or minutes. The SLA for me hitting submit and seeing the tweet on the page is measured in milliseconds because I don't have to process that immediately. I don't have to do everything in the critical path. I accept that. My user interface is going to show that, hey, it's showing up. And at a later point in time, this is going to be published and sent and everything in that regard. A little bit of complexity in the user interface means that, oh, I have to do, I don't know, fraud detection using some machine learning that is quite expensive. I can do that. So the question here is, why bother? I have auto scaling. Here are some rules. Let's do that. We're done, right? Well, the problem here is that sort of, because to start with, you can auto scale the things that you own. What about the things that you don't own? I need to run some image recognition on the process I'm running. I'm not doing that myself. I'm sending that to a third party that does invoice OCR or parsing or whatever they do. They're not going to let me monopolize all of their capacity just because the guy from Thailand came back and submit everything all at once. And what happens if I need, for example, to run a check against the Swedish post office? Because I need to verify if an address exists. And I have a really nice API that I want to be able to call. But the Swedish post office isn't really interested in letting me have infinite capacity. So we don't want that. Also, because in the end, you're going to be hit with a massive bill. Oh, you spiked. More resources, more things that can fail in really interesting ways. Not fun. So, background operations are the limiting factor, especially at third parties. So, we want to avoid that. Otherwise, especially if you have in the backend complex queries, so we need to scale the database, and now we have to worry how to manage the state of a distributed database and what are the limits that are involved in that. Or I can use caching, and then I have to talk about caching validation, all sorts of other stuff like that. And at the end, remember, there is a human at the end of the line, and they are waiting for me. And there's been studies made on that, and even 100 milliseconds of additional latency is meaningful. And if you have a lot of complexity, if you integrate with, you're doing a lot of stuff, then it's really hard to beat the clock. Move the clock out of the critical path and you're done. So let's talk about what this means and how it's actually going to work. The whole idea is that we put it in a queue, and something in the backend will pull the stuff from the queue and process that. In the front-end dimension, we just register acceptance, show the UI, and we're done. Now, here's the interesting detail. We can look at the queue drain rate. Not enough and more workers. Isn't this exactly the same as autoscale? Not quite, for two reasons. Reason number one, you can have more leniency. Or I can see that the drain rate, the amount of things that I pull from the queue isn't happening fast enough. But I don't have to react to that immediately. I got time. So any temporary spike is smoothed. There are also a lot of nice things in queues that I can log all the queues so I can understand better what's going on. It says, oh, this is a slow operation. Or I can see that we have a big spike at that point and that impact this third-party system or this backend database or something like that. Important about this, when you log messages and in general, think about privacy. With the queue, you also have more options. For example, let's say that I want to process events on not events, commands on orders. One of the things that I may have to do is do validation. But instead of doing validation one item at a time, I can go to the queue and tell it, give me 100 messages, and I will process all of them in a single batch. So any third-party calls that I have to make can be batch. It's so much more expensive, so much more efficient than a per message operation. If you don't use a queue, this becomes seriously complicated issue. Really hard. Now you don't have to use a queue. Use multiple queues. Use them based on topic, something like that. And this is a great example. Purchases from Brazil. Now I have just that aspect of my system may be slow. And maybe it's okay. Maybe currently there is, I don't know, postal office strike in Brazil. And I cannot process those sort of errors, but it doesn't have an impact on my whole system, just on the Brazilian worker nodes. And Spiker Smoothed, I mentioned that, and this is really interesting. These two. Message processing code is amazingly simple. There's no UI. There is only computation, which means that the amount of things that you have to keep in your head are drastically reduced. Because of the way that you process the events, the messages, then there is no shared state. You don't have to deal with session caches, stuff like that. It's much simpler and easier to work with. And on the front end, it's also simpler. You just read from storage, cheap queries. Everything is fast. I don't have enough time to go over in depth, but handling errors in queues is also simpler because you have the input, the initial message that was put in the queue, and now you can handle that. For operations, spin any node, run it, run on the old node, no downtimes. From an operational perspective, a queue is a really simple mechanism. It makes it very simple to operate in production. They also tend to be extremely reliable. You have really interesting metrics that can tell you. You can look at what's happening, which is really nice and doesn't require you to add a lot of complicated infrastructure or a runtime tracing or any of those sort of things. The built-in tools in the queue will already give it to you. So the front end, put the prepared data, and this gives me proper separation. The challenge is actually in the user experience. In most cases, you can fake it. Look at something that happened at the background and just pretend it happened in the foreground. Have the plan in place what happens if it fails after the fact. Or you sent a tweet. For some reason, all of my examples today are about Twitter. You sent a tweet and it contained a bad word. So we show it to you. In a few seconds, maybe a few minutes, we give you a notice, hey, you cannot use the word cucumbers on this social network. Okay, some superpowers that are going to give you major benefits. If everything is CRUD, most of everything is CRUD in most applications, just do the setup until you get to the point where you can actually do something. Then we get a request, we process that, and then you're done. It's important to understand what is reasonable time frame to wait, and how do you manage that. So if I'm sending a request and the average response time in the backend to process that is under 10 seconds, don't even bother doing anything special. Say I accepted that. On the rare cases where this would fail, raise a flag after the fact. No need to do anything special. If this takes more than 10 seconds, if there is scenarios where it would take minutes, hours, something like that, you may need to have special special UX for that. But generally, even if you sleep, it doesn't matter. Those tends to be rare. And if the end result is okay, we're good. Here's another aspect. It's okay to say sorry. I have to accept orders on Black Fridays. My goal, accept all the orders. I don't have to charge the customer. I don't have to provide a service yet. I have to record that the order happened. Afterward, at leisure, I can process all of them. What do you mean if I run out of inventory? Well, okay, I'm sorry. Actually, I'm not sorry. I have a chance to do a whole bunch of interesting things. For example, I'm going to say sorry to all of the people who came in last, all of the people who paid the least, or I can send them, hey, we don't have model X, we have model Y. The difference is $5 to you. For me, it's the same cost. So I'm just going to send it to you, the new model, which is cost slightly more, and you will be happy with that. And the idea here is that by not tying myself to the commitment, I acknowledge and process the order immediately online under pressure, I massively reduce the amount of complexity that I have to deal with. What happens if I have just one item? Well, I don't care. Same behavior. Put it in a queue. This is the amount of complexity that I need to do. But there is one winner. How do I know who the winner is? Well, after the cutoff date for the auction, I'm going to run Discord. Give me all of the bids that were passed before the cutoff date, and then give me the first one. That's the winner. We're done. By the way, we also have an audit log. If we are contested, we have to go to court about that. If I have a complex business rules about, oh, I have to, you submitted a bid on the Mona Lisa. Do you have enough money for me to consider you here? That might involve calling to your bank. Well, I don't care about that. I can do that because there's a difference between accepting and processing. Another thing that is important is that people seriously undervalue the power of being stupid. Stupid solutions are easy to scale. If you're not doing something complex in a critical path, then, well, it's really easy to scale. Do everything is possible to move processing to the background. And then you can basically copy paste okay, here is the background worker that is running. I might even start the background worker as a separate process on the web node and only move that to a separate worker, separate machine, Lambda, whatever, down the line. But having the data go through a queue, making sure that the entire architecture is built around simple only asynchronous processes, things that users waiting for are only allowed to do very simple things. And anything slightly more complex that is in a queue is a major factor in actually being able to say, oh, let's spin 10,000 nodes in order to handle the work on the queue. Here's a great example. I mentioned the reimbursement systems. So the employee needs to upload the invoice. And then we need to do some OCR. And then we need to update the system of the pay cycle. How do you do something like that? Well, as much as possible, I don't want to do any of that. So what I'm going to do, I'm going to hand a pre-signed URL to the user. Then the user is going to upload their invoices to S3, for example. R2, whatever storage you use, all of them have the capacity of a user to upload directly to them. And then I have a trigger on a file upload that would cause me to run OCR. If I'm using AWS, I can have that happen automatically. So I have S3 that generate a pre-signed URL. The user upload directly to there. The upload generate an event that is put in a queue that is triggering a recognition or any OCR that you use that automatically would output the scan OCR output to another queue. And the only code that I have that is running is putting that in my system. That's it. Now, why does it matter? Because if I have the guy who is now uploading 10,000 invoices all at once, that's not me paying the compute for or the bandwidth for update all of those and then push that to S3, all of that. All of that is the responsibility of the cloud infrastructure, whatever services they have. I'm not running that. I'm not thinking about that. And to close that, I want you to go back to PHP as it was originally conceived. Stateless, local, and basically read stuff from the database, show it to the user, and you're done. And all of the complexity shifted elsewhere. And PHP has a really bad reputation, but as an architectural style, it is amazing because its status, it doesn't let you do much. So you have to push all of the actual complexity to the background. And if you look into scalable systems, Facebook is running on PHP. Now they're not running on, they had the custom PHP runtime and Hive, I think it's called, or everything like that. But a lot of that is about not doing too much. And with that, if you have any question, we're very happy to take them.
Awesome. If you have any questions, we are here for giving answers. I mean, Oren is here for giving answers. I must admit that you have pitched queues so much that now I'm feeling like writing some queue-based system.
Yeah.
Probably it is not so common. Like most people are still thinking about simple request response pattern, right? And
yeah, and the issue with request response patterns is the response. What are you waiting for? Because what happened is that you have, let's see if I have this here, pen. So you have a request, and now I have another request, and then I have another request, and another request, and another request. And the response at this time, the user is being very, very sad. And you will forgive me if I'm doing very bad drawing. But the user is very sad because something is wrong. They have no idea. And now, at best, you're going to see, hey, this is going to return a 500 error with some message. But remember that in the end, you have a timer, either explicitly because of request timer or because the user is going to be very sad. And that's going to be a real killer for us in how this is happening.
exactly. And my finding from your talk is that the scalability improvement is lying maybe somewhere in the technical part, implementation part, but it is also like the scalability may be driven by business, like the business process, how we can drive the user through the journey on the platform, because business can really gives us suggestions how we can treat him to not be waiting for immediate result, right?
Consider the case that almost all business processes are asynchronous in nature.
Exactly.
And the reason for that, if you go back even 20 years, I could send you, let's say I want to order a pizza. Well, 20 years ago, I would go to a fax machine and tell you, hey, I want pizza with cream cheese and onions, and fax that to you. And you would process this. And this is a great example of a queuing system. And at the end of the day, you have all of the usual things. If you think about how money is transferred, I want to pay John $100. Well, I'm not. It may look like I'm doing that live, but it doesn't actually happen this way. It goes through multiple queues and checks and all your customers and tax evasion rules and all much of other stuff like that. So that's how all of those things are actually happening. At one point, I had a customer pay me, and the money went poof somewhere in the middle. Apparently, it was enough. That payment was enough to trigger the oh, you paid too much for this guy this year, so you have to give me IRS authorization to continue paying because he may be evading his tax or something like that. And suddenly you realize, wow, this is the example that we always talk about of transactions with money and withdrawal and stuff like that. So much not the case.
Not the true indeed. Yeah. So if you want to scale your system, go to business and they will give you some suggestions, maybe how you
Yeah.
can process it, the customer. That's super nice. And by the way, don't you feel that maybe we are teaching and being learned design of web apps, especially in the wrong way? Like we are all, I mean, there are dozens of frameworks that are still based on synchronous communication, and it is absolutely normal and typical. Maybe there are times to develop frameworks that are in hard asynchronous using some queues underneath.
There are there are those, and service platform particular is one such example. And but the real question here is, do you actually are you actually going to need that?
Mm,
Because we're talking about scalable systems, but I'll be honest, most systems should be able to run just fine on Raspberry Pi. This is literally not science fiction. If I'm able to write 200 lines of code and process hundreds of thousands of requests on Raspberry Pi, then the issue isn't with the complexity of the data, isn't with the size of the data. I had a benchmark where I'm processing terabyte of data and processing on RavenDB on Raspberry Pi running on a terabyte database. And you know what? Most of the time is spent on I/O because that machine doesn't have a terabyte of RAM. But it's still visible to hold most most production systems. And the issue here is when you start tacking this on top of this, on top of this, on top of this, and suddenly the weight of it all become too much.
true. So it is all in the context of your particular product and system, right? If you are watching this and you are architect or you are designing a system, do not start adding all these features just because it sounds nice. Like you said, stupid solutions are easy to scale. That's the
Yeah,
quote of the
but
day.
here's the problem. If you write this sort of code and you know that all of you're doing is reading from a local DB, show to the user, and everything else you already explicitly handle and manage, then that's okay.
Right.
You're done, and this is cool. The problem here is that you have these incredibly intricate systems where everything is happening inline, and suddenly especially, and the problem is especially when you're talking about what sort of promises you gave to the user, either implicitly or explicitly. There's also another major issue, and that issue is that the tendency from oh, this is a computer so it must be exact, and then you realize that, oh, you know what, the notion of millisecond precision for business systems almost never happens. I don't actually care if the payment for if I submitted the payment at 1659 or 1700, typically doesn't matter. Maybe you missed the due date. Oh my God! I would backdate something 2 minutes back. No big deal for anyone. And but we think about it. We think about a millisecond from the technical perspective matters. From a business perspective, it doesn't. I remember at one point I was doing errands with my uncle, and he went to the post office on a Friday night at 10 p.m. And why did he do that? Because they would clear the post box at 8 p.m. and the next day at 8 a.m. So if you would put the check in the post office at 8 p.m., at 10 p.m., then it would be processed next week, but would be counted as it happened earlier. So it wouldn't be late on his rent or something like that. But then that's just the way it is in business and in life. So milliseconds doesn't matter, but the moment that we make everything synchronous and one step after another, we have to face that issue.
That's true. Awesome. I feel inspired. I will just immediately start coding some queue-based system.
It's a lot of fun.
Exactly. Obviously, it gives another issues, right? It is not only super probably nice, and then you have some another issues to solve, but still, it sounds like a fun. We have no more questions, and the time is also now to close probably the session. So very much thank you for being with us. It was a pleasure, and I hope we will meet somewhere, as I'm saying to anyone.
Yes. Thank you.
Thank
Goodbye.
you. Goodbye.